Welcome to day 1 of Math 135, and we're going to start out with some basics of graphing. This course is going to have an awful lot of graphing within the class, and I think that sometimes we just overlook the bare-bone basics. I know that much of what I'm talking about today you have already worked with in an Algebra 1 or an Algebra 2 class in high school. However, sometimes we just kind of overlook the basics, and so I want to make sure that you've got a really strong grasp of what we're doing here so that it'll all go much more successfully for you. Okay? Hey, there should be a handout on Blackboard, and you might want to bring that down as you work through the lesson with me. And especially because we're starting out with some nifty little stories and graphs. Now what you might want to do is, in just a moment, pause me so that you can see if you can match these up. What I've done is given you 4 stories and 4 graphs, and you're supposed to match up the graph with the story. Now just to make sure that we're all kind of clear on what's happening, your horizontal axis is showing time, and these should be equal increments. I didn't say if they were 10-minute increments or 30-minute increments. And then I have distance from home. There really is an O there, you just can't see it. The distance from home, and I've marked off increments. I didn't deem it important to tell you whether it was miles and how many miles for each increment. So, take a few moments and see if you can match up which story might go along with this particular graph. And if you want, as I said, pause it and then get me started and we'll go through them. Okay, now for the first one that I'm looking at here, we go up, we're increasing our distance away from home, and then it goes down, and it's kind of interesting here that we hit the x-axis. Now what that means is if we hit this horizontal axis, then my distance from home had to be 0, which means I guess I went back home. And so the story that goes best with that is that you're riding to class, you see some clouds up in the northwest, and you decide to return home. So here is where you realized, ooh, weather's not looking good. You turn to go home. How do I know? Your distance from home is now decreasing. And then you're at home, then it increases as you got in your car to go to campus. Okay, you kind of getting the gist of this? It's an idea of if you understand what the graph is telling you. Okay. Going on to the second one, we see a little bit different. We're going away from home, and then we just kind of hold steady for a little while, and then we continue going away from home. And the story that I picked to go along with that is that you stop to chat for about 15 minutes with a friend. So right here is that spot where you're stopped, because no longer is your distance from home changing. It's not increasing, it's not decreasing, it's remaining constant. Okay. Next guy, your distance increases, it decreases, it increases, and it decreases. I thought this one sounded like a fun story. Well, as long as I'm watching it, not living it. You're riding your bike to campus. You realize you set your alarm 1 hour too early. And so that's when you decide, ooh, I can go home and sleep a little bit more. But partway home, you decide, oh, I should go to the library and do some homework. So you turn to go back to campus to be that responsible student. And all of a sudden you realize, dang it, today is Sunday. And you head home, very angry at your mistake. All right? Last graph. Now, by elimination, there's only one story left, but let's see how it might go along with it. What's kind of interesting is this is the first time that we see a curve happening here. And it's kind of interesting. You notice that your distance from home is always increasing. Okay? Now, technically, we've got about the same increment between our points here horizontally, and that horizontal increment is our time. But vertically, you can see that you have the biggest gain in the beginning and then less gain and less as you go along. Okay? So, as you look at the story that I put with this, you start writing a little bit too fast. I know I've done that. And then you're just a little worn out and you're slowing down. Now, you might think, what is this crazy woman talking about? We're graphing time and distance, so how can she be talking about pace? Now, you know, pace is essentially velocity. Well, wouldn't your velocity be, say, miles per hour? Now, it could be it could be feet per second or whatever, but if you're doing miles per hour, you realize that it's a ratio of distance over time. And in this particular case, what's interesting about that is that that is essentially your slope all the way along that particular ride. Okay? So, hopefully you've had fun and kind of started to think, which is something I want you to do all through this course. And now let's get into a little bit of the history. Like, where did this whole idea come from about graphing? Well, you might know this gentleman. His name is René Descartes. Okay. You know, you don't want to get Descartes before Deshorse. Sorry. And some people know him from a phrase, I think, therefore I am. Now, some historians will tell you that maybe Descartes did not say that, not verbatim. But anyhow, you might have heard that particular phrase. So, Mr. Descartes here, he's a philosopher. And I've never been a philosopher, but my guess is your job in life is to just think. And what Mr. Descartes liked to do, according to folklore anyhow, is he liked to lay in bed late in the day and just think. And since that was his job in life, I guess he was being productive. Anyhow, let's put Mr. Descartes to bed here. We're going to lay him on his side, and he's looking up at this ceiling. We're going to pretend that this is the ceiling in his room. And he's just sitting there. Maybe at this particular moment, he doesn't have any awesome thoughts going through his head. And so his attention is grabbed by this little fly. I know you may have trouble seeing that fly, but there's a little bitty fly going on here. A little hard to see in real life, too. So he's lying in bed and he sees that fly, and the fly kind of buzzes around and boop, lands. And now he's got his attention, and then the fly kind of buzzes around a little bit more and lands, and there he is. Now, of course, you and I would probably be going looking for the fly swatter, but that's not what Descartes does, you know, because he's kind of in a different realm. He starts thinking. He starts thinking about the location of that fly and how he would like to describe where that fly is sitting. Yeah, he's not like us. So anyhow, he starts thinking about, well, what if I put a number line up there on my ceiling? Now, I have no idea where he might have decided to place his number line. I'm going to just place it kind of down the center there. Now, what's interesting about my number line, and I hope you've seen number lines before and pondered them, this line has every real number located somewhere on that line. Now, we like to show just these integers, -1, -2, 0, 1, 2. We like to show those numbers, but it really has every possible real number on there. So like square root of 7 is there, and 83, and 2.9. So with that number line on the ceiling, what Descartes could do is he could talk about the location of the fly horizontally. Okay? But then he realizes, by itself that's not sufficient. So how about if I take another line? Okay, it's another number line just like the one I started with. And what I'm going to do is I'm going to turn him so that he's perpendicular to that first line. Now, that was one of the cleverest things that he did. As he put those guys perpendicular to each other, he just made things work out so nice for us in so many ways. And now what he could do is, wherever that fly happened to be sitting, he could assign two numbers, and those two numbers would describe how to get to the position of the fly. So for example, right now it appears that my fly is very, very close to a position. And anytime you're going to give a position, you kind of need a reference point. Well, our reference point here is this point where the two axes meet, and that's called the origin. So that's the reference point from which we move in order to get to certain locations. And so we could say, well, from there, go 7 to the right and go down 5. And then, boom, you got the fly. Go 7 right, down 5. Somebody else comes along and says, well, we could say go down 5 and then go right 7. Okay, we get to the same place. But in mathematics, we like having all these shorthand ways of writing things so that we don't have to write very much. So Descartes decided, you know what? Here's how we're going to write this. We're going to say that that fly is sitting at 7, -5. And it was decided that what we would do is put these locations in an ordered pair. I know you know this, but it just kind of helps to get it all down in a real comfortable setting. This is going to tell you your horizontal motion. This is going to tell you your vertical motion. And then we all look at that. We all know exactly how to get to that fly. And if that fly moves, and maybe he's sitting over here, and he's kind of in between integers, that will happen. So I might decide, well, let's see here. I think he is at -8.47, -6.01. You say, what? Well, that could be where he is. And the point is that no matter where that fly lands, there is exactly one ordered pair that is going to name that location. And it is kind of interesting because we can look at the coordinates and know that in relation to that origin, he's left and down. Remember, that's what the negative signs are doing. They're giving us the direction that we move. Okay? And lastly, maybe we train this fly. Descartes getting to know this fly quite well. And maybe we tell this fly, we want you to go to 6, pi. And the fly, being a very smart fly, says, absolutely. And he goes to the one and only location for 6, pi. Because it's a two-way street going on here. Every single point in this plane has exactly one name. And every ordered pair has exactly one location. Very powerful stuff, and it opened up this wonderful visual process for us. So we thank Mr. Descartes for that. And in fact, you might recall that it's actually called the Cartesian coordinate system, after René Descartes. Okay, so now what I'd like to do is go and do some really basic graphing. And I know you might be biting at the chomp to get into the more complicated stuff. Don't worry, we will. But I still want you to have some very basic ideas. So we're going to graph each of the following equations and identify x and y intercepts. We'll talk about what those are as we get over to the graphs. Okay. Oops. The very first equation that I want to graph here, let me get everything kind of moved into a good spot, is y equals 2x plus 3. Now, I know that some of you totally remember graphing these from high school, and you are ready to go. You're going to put that 3 in there. You're going to move with a slope of 2. Yay. Okay, slow down. Because what I want to do is spend a few minutes, remember, on the basics. Okay, so here's my equation. And do you know what it means when we say graph the equation? What are you really doing? Well, you see, as it turns out, if you look at this equation, you realize I can't solve that for a single pair of numbers. Like there'd have to be an answer for x and an answer for y. And as it turns out, there's infinitely many pairs of possible numbers to make this true. So what I want to do is make a table of values. Now, I know that this is the most basic way to graph, but I want to spend a few minutes with this because when all else fails, all of your high-powered maneuvers are not working, this is always the way that you punt. Okay? So let's see here. What if we get to pick numbers? That's what's really nice. And I'd like to pick some numbers for x. So what if I pick 0? Now what that means is that if I put the 0 in here, 2 times 0 plus 3, I get that y is 3. Now what that does is it tells me one pair of numbers that will make that equation true. When x is 0, y is 3, that is a true equation. So I come over to my graph and I say 0, 3. There we go. Okay. Now, is that enough for me to know where all the other points are? No, I need some more. Well, what if I let x be 2? Well, remember, what you're going to do is replace it. So we have 4 plus 3, we have 7. Okay? Let me find several more here. What if I decide to put in a negative 2? Then I'll have, what, negative 4 plus 3, we'll have a negative 1. Okay, and how about if I put in a 3? We get 6 plus 3 is 9. Okay, so let me go ahead and put those in as well. So we have the point 2, 7. The point negative 2, negative 1. The point 3, 9. And you look at those and you say, okay, I kind of see a pattern going on here. You might want to put in some other values, like if x is 1, we get out a 5. Hey, can x be 1/2? Well, what's 2 times a half? 1 plus 3 is 4. So 1/2 I get out of 4. You know, as it turns out, I can technically put any number in there for x that I want. And you might not realize that that's an important observation, because a lot of times students love to put 2 or 3 points on a graph and then just connect the dots. Well, why are you connecting the dots? The reason I can connect the dots here is because x can be any real number at all. And we had, what, 1, 5 there? And there we go. Give me 1 second. I want to make that thick. Okay. And so I actually can connect that and have all of those points. Right? As it turns out, I missed that just a teeny bit. There we go. Okay. Now, let's talk a little bit about what we see here. We have what are called intercepts. And back on the previous screen, I said I want you to find those intercepts. Well, an intercept is where they intersect. I'm sorry, I didn't make up this language. So a y-intercept is where the line crosses the y-axis. Y-intercept. And you want to give it as an ordered pair, because remember, Mr. Descartes got us all set up on this whole ordered pair thing. And the location for that is at 0, 3. Okay. Well, now I need an x-intercept as well. Remember, generally we call the x-axis the horizontal axis, and the y-axis is generally the vertical axis. Technically, you can name them anything you want, but if you're going to do other than the x and the y, you definitely need to let us know. Now, I would like to know this x-intercept, and I can see it visually right here, but I'm not 100% sure what that order pair is, because I'm hitting in between two integers. So if I want to know what it is, here's what I need to think. Well, if it's on the x-axis, that means I did not go up or down at all. He has a y-coordinate of 0. So I can come over here to the equation and say, all right, let y be 0 and find out what the x value should be. So we put the 0 in here on the other side for the y. Solve this equation. -3 is equal to 2x. X is equal to -3 over 2, or -1.5. And you look at your graph and you say, yeah, that looks like -1.5. I'm totally good with that. So we could say -1.5, or you can say the -3/2, whichever way you prefer. That's my x-intercept. I kind of like knowing those intercepts because those axes are so important to my whole graphing system. I like to know where I'm hitting those. Now, one other thing I want to make a point of before we leave this first graph is, what am I looking at? You know, because you've gotten used to graphing these things in the past, and you may not even realize the power of this. How many points are on a line? You know, you probably had that back in geometry class. This line is made up of infinitely many points. And Mr. Descartes managed to find a way to give a name to every one of those with an ordered pair. And as it turns out, every single one of those infinitely many points along that line will make this equation true. So if I happen to pick, well, looks like 3,9, and actually we already worked with the point 3,9. But I picked the point 3,9 because that's on my equation, or it's on my graph. And I come over here, put in the 3, I get y is 9. So it makes sense. Every single point on that line makes that equation true. But there's something else going on as well. If I pick, say, a point out here that's not on the line, let's see here, -4, 5. Will -4, 5 make that equation true? Well, let's see. The y-coordinate is 5. Does that equal 2 times -4 plus 3? You might think at first that it does, but watch the sign really carefully. This is a -8 plus 3 is -5. No, this is not true at all. And so what's very interesting is that while there are infinitely many solutions to this equation, there are also infinitely many non-solutions. Okay? And you see those as well. Okay, y is equal to -4. What's kind of funny is sometimes when the equation gets simpler, it seems more complicated to us. Okay, so let's make a table of values. Y is equal to -4. And I'm going to make, you know, I called it a table of values. Your teacher might have called it a t-table. So in my t-table, I say, well, y is -4, y is -4, y is -4, Do you realize that that equation is telling me y is always negative 4? And then you say, well, what's x? Well, apparently x can be anything, because if I take the point 0, negative 4, I don't have anywhere to put the 0. The negative 4 makes that true. Okay, well then maybe I have 3, negative 4. Maybe I have negative 5, negative 4. Let's see what happens when we try to plot these. Okay, so I go to 0, negative 4. I go to 3, negative 4. I go to negative 5, negative 4. Okay. And if you think about it, I could try 1, negative 4. I could have 5, negative 4. I could have 10, negative 4. And you soon realize, oh, wow, look at where these are. If I could hit them better. They're all lined up in this lovely line running right along there. So what I have is this nice horizontal line going across there. And you know what? It does make total sense, because it's saying y is always negative 4. Well, remember, the y number is your vertical move. And so it essentially says just move all your y's, boom, down to negative 4. Okay, well, hey, what is the y-intercept in this case? Well, you're looking at them. My y-intercept is 0, negative 4. What about my x-intercept? Well, now the x-intercept is where he crosses the x-axis. And you see that I don't have that happening right here. Will he ever cross the x-axis? No, because you know this line is going to stay as a horizontal line. He's going to stay 4 units below all the time. So in this case, there is no x-intercept. It's not real common, but it does happen in our graphs sometimes. Okay. Number 3. Oops, sorry about that. All right, on number 3, we've got a new equation here, y equals 6 minus x squared. Now, if you're real good with your algebra from the past, you know that x squared is suddenly going to change things. But you might not remember how it changes it. You might not know what this graph is really going to be like. So let's make our table of values. Now, as we go on through this course, I'm going to want you, by the time we get to the end, to look at that equation and just say, boom, I know it's this shape, I know it's located here, I know it has this, I know it has that, and give me all the features. But for right now, we're assuming I'm not ready to do that yet. I just want to look at the very basics of graphing. So I say, well, what if I let x be 0? 6 minus 0 squared is 6. What if I let x be 1? 6 minus 1 is 5. And then it might start dawning on you, well, wait a minute, what if I used a negative 1? Because you know that square is going to do something here. Negative 1 squared is 1, so 6 minus 1 is 5. Okay, well, let me take a peek at that. So I've got 0, 6, I have 1, 5, and I have negative 1, 5. Kind of looks like a little triangle going on here. Do you really think it's a triangle? And this is where you have to be careful about just randomly connecting points, because when I see that, I'm thinking, either I've totally messed up or this is not a straight line. I better get some more points. Okay, if x is 2, 6 minus 4 would be 2. What if x is negative 2? I would have 6 minus 4, I'd have 2 again. Okay, so let's put those guys in. I've got 2, 2, I've got negative 2, 2. Well, that's looking pretty cool. Hey, you know, I do have my y-intercept. It's always nice to have a y-intercept. And you know, I'm not ready to talk to you yet about whether I could have more than one y-intercept. For right now, just realize I'm only going to have you graphing with one y-intercept. Okay? But it'd be nice to have my x-intercepts. X-intercepts. Now, if it crosses the x-axis, and I'm guessing it looks like maybe it crosses twice here, it means that the y-coordinate has to be 0, right? Okay. Well, let's see here. If the y-coordinate is 0, I'd have 0 equals 6 minus x squared. Add the x squared over. And so you ask yourself, well, what squared would give me 6? Well, that would be, remember that old plus or minus thing? Now, technically, that is the number. Remember I told you Mr. Descartes gave us that real number line that has everything on it, including these scarier looking numbers. Okay, now when it comes time to graph it though, they kind of forgot to tell me where square root of 6 was on the number line. But what you can do is turn on your common sense. You know it has to be between 2 and 3. Would you agree to that? Because 2 squared is 4 and 3 squared is 9. So you at least know that it's falling somewhere between 2 and 3. And if you'd like, you can get a calculator and get a better approximation. It's around 2.4. Well, you know what? Then I will just do this. And over here at about negative 2.4. So I do have two x-intercepts in this case, and my x-intercepts in this case are square root of 6 comma 0 and negative square root of 6 comma 0. Kind of interesting. Last time I had none, this time I have 2. And then, as it turns out, I can kind of connect the dots with this nice, pretty arch kind of curve. Some of you might know all about that curve. Hey, and any time you're a little bit unsure about what your graph is going to be because it's a curve, it simply means you want to put more values in your table. Remember? Now, hopefully you will look at that equation later on and say, I know that's that nice arch curve. I know he crosses at 6 and opens downward. But for right now, make a table of values. Okay? Well, now we have x equals 5. X equals 5. Well, you know, that kind of sounds reminiscent of our one the time before here. X equals 5. You know, it kind of sounds like the y equals 4, but he's different. So let's see here. In my table of values, x is 5, x is 5, x is 5, x is 5. X is always 5. Well, what's y? Anything you want. It can be 0, it can be negative 2, it can be 5, it can be pi. We'll make it negative pi. And then I come over to my graph and I say, I can have 5, 0. I can have 5, 5. 5, negative 2. 5 pi. And I put that a little high. I can put that 5, 2. 5, negative 4. I can keep doing that all day long. And you soon realize, oh, he is a straight line, and he happens to be this nice vertical line. And his x-intercept is 5. Although, be very careful. When you're writing this x-intercept, you should say 5, comma 0. Give it as the ordered pair so we know the exact location of which you're speaking. What about a y-intercept? Is he ever going to cross the y-axis? Now, you know, I want to pause here for just a second. What we found is that our x equals 5 was this vertical line, and we had y equals 4 was this horizontal line. And some people love to just memorize. Well, you'll find I am not much of a memorizer. I don't like to use this for storage. I like to use it for processing. So what I'd encourage you to do, because you see, years of experience have told me that sometimes your memory fails you. Instead of memorizing, x equals a number is always vertical, y equals a number is always horizontal. Instead of memorizing that, take just a moment and think about what these equations mean. If I see y equals 4, that means your y coordinate is always 4. We don't care what your x coordinate is, your y coordinate is always 4. And if you just ponder that and plot just a couple of points, very quickly you've got that horizontal line. And you reasoned it out. You didn't rely on your memory being correct. For x equals 5, you just simply think, I'm always moving to the right 5 and I can go up or down any amount I want. Oh, that's that vertical line. Now, you do what you want to do, but I encourage you to think about what these are instead of just memorizing. Okay? Now, I'd like to do probably just one more, maybe two. We'll see how our time goes. Negative 3/5 x plus 4. Now, again, I know some of you are like, oh, I can do this. I'm ready to go. Great. Okay? But I'm still going to make my table of values. Y equals negative 3/5 x plus 4. I want to know where he crosses the y-axis. It's always convenient to try to put that 0 in right away. And that zeroes that fraction out, and I get 0.4. You know, since I'm in control here of the marker, power of the marker, I get to pick whatever I like. And I don't want to put a 1 in there because I don't want to deal with fractions. Now, there's nothing wrong with it. That coordinate axis system includes all those fractions. But if I want to make nicer numbers, I can say, hey, let's let x be 5. Because then I have negative 3/5 times 5 plus 4, and that ends up being 1. Okay? So you get to choose. That's one benefit of making the table of values. Well, since that went well, how about using a negative 5? Y equals negative 3/5 times negative 5 plus 4, and I believe that's going to be a 7. Okay, so let's take a look at those points already. We have 0.4, 5.1, and I have negative 5.7 sitting up about here. Yeah. I can double check it by finding some more values. Boy, I drew a bad line, didn't I? Now I would like to get my intercepts. I know my y-intercept is 0.4. Now how do I go about getting the x-intercept? You know, this is one of the most important things that comes out of this lesson, along with the basic concepts, because even when you're really working with the higher level functions, we still find x and y intercepts, and we still find them the very same way. We find them with the zeros. So in order to find that x-intercept, I need to put 0 in for y. Okay, well that would be 0 equals negative 3/5 x plus 4. Okay. Let's add the 3/5 over. And that's not much fun. You might remember that essentially I'm going to divide the 3/5 over. Okay, and dividing by 3/5 is the same as multiplying by 5/3. And I get x is equal to 20 over 3. What? So apparently my x-intercept is 20 over 3 comma 0. Now that's one way to write it. You might also say, well, that's 6 2/3. Right, the mixed number. And in this case, the mixed number is kind of nice. I actually hit that reasonably well, that I'm at about 6 2/3. And I love how the picture should all come together to make sense for us. Okay? Now this last guy that we'll graph, 2x plus 5y minus 15 is equal to 0. What I would kind of like to do with him is add the 15 over, just because I'd kind of like to see it that way. So 2x plus 5y is equal to 15. Okay? And I always kind of like it when they're sitting in this particular form, and when we work with linear equations, we'll talk about what form it is. Because if I want to know my y-intercept, I put 0 in for x. You're always putting 0 in for the other guy. Well, if I put a 0 in here, that totally wipes that away, and 5y is 15, well, that would be y is 3. Now I can do the same thing to get the x-intercept. For an x-intercept, I let y be 0. If I put a 0 in here, that goes to 0, and I have 2x equals 15. Well, that means x is 7.5. Okay? Then I might want to pick just one other number in there somewhere. So I might say, okay, what if y is 2? Just see what happens if y is 2. So I have 2x plus 5 times 2 is 10. 2x is equal to 5. X is 2.5. You might remember from back in Algebra 1, your teacher, when they started you with t-tables, generally recommended at least 3 points. They might have expected you to come up with more. You really need to do that in order to make sure you haven't made an arithmetic mistake, or maybe this is a curve but you didn't realize it was a curve. It just helps. And then if there's any question, add in a few more points. Okay, so I've got 0, 3. That's my y-intercept. I have 7.5, 0. That's my x-intercept. Now this guy is a line, and so hopefully it's all going down through there. I have 2.5, comma 2. Does that seem to be kind of in line with the other guys? Yeah. And I'm connecting all the dots. I'll growl at you later because you don't just randomly connect dots. But in this case, it does make sense because I can put in any value for x, any real number at all, and then depending on that value, I'll get a value for y. Okay? And remember what I'm looking at. The whole point is this is a picture. It's a visual picture of every possible order pair that will make that equation true. Okay? It's really very powerful stuff, and we thank Mr. Descartes for what he's done for us. So now we're at our recap. What have we kind of picked up here today? First off, the Cartesian coordinate system. Now, why is it called Cartesian? That's after Descartes, René Descartes. The Cartesian coordinate system shows the relationship of two variables, ordinarily called x and y, by showing pairs of numbers that will make the equation true when you put them in simultaneously. Okay? And of course, you had a chance to get a feel for what each of these could mean as we went back and looked at our distance from home versus the time and riding our bike to campus. Okay? Number 2. As you try to analyze what you see in the graph, focus on each of those dimensions individually. Again, back to the idea of riding your bike away from home, the distance and the time. Pay attention to what is actually being graphed on each of those axes. And then lastly, you're going to learn in this course a lot about graphing. And when we get to the end, I want you to be an expert at graphing. But you do need to realize you can always back up and make a table of values if you want to. But I do want to warn you, and you saw today, not all relationships are linear. So don't just plot 2 points and then connect the dots and think you're done. No. Pay attention to the clues in the graph or in the equation, and if need be, make an extensive table of values. Okay? Hopefully you won't need to do that a lot, but it's always your backup plan. Okay? We'll have lots more to learn about graphing as this course goes on. I do hope you take some time and get really comfortable with all these basic ideas. See you next time.